welcome. In this lecture, we are going to recapitulate frequency domain design of analog voltage mode and current mode control, and this will give, provide like a path for going for digital control design. So, in this course lecture, we are going to recapitulate continuous time small signal diagram under voltage and current mode control, frequency domain PID controller design for voltage mode control buck and boost converter, then frequency domain PI controller design for current mode control buck and boost converter, and summary of key design step for analog voltage mode and current mode control. So, here we will first want to recall the voltage mode control buck converter, and we have discussed this diagram multiple times, and this is a sawtooth waveform to generate the duty ratio. Now, if you go for digital voltage mode control, what are our primary loop shaping objective? So, you can see this is our loop transfer function. Loop transfer function. Then the loop transfer function is the product of the modulator gain, and this modulator gain is coming for sawtooth waveform, it is 1 by Vm, that is 1 by the peak voltage, then Vin by alpha, and there is a ESR 0, and then there is a double pole that is coming, and this is a controller that we have to design. Then what is alpha? Alpha equal to R plus R equivalent by R, and R equivalent is what? It is nothing but the R on state plus RL. So, throughout this lecture we will be using RE. Now, we know the ESR 0, then omega 0, Q factor and ZC. So, I am not going to repeat again. How to design, and you will get all this detail in lecture number 30 in NPTEL, the control and tuning method. Then PID controller tuning for this voltage mode control we want to do for stable pole zero cancellation. So, we can write a practical PID controller that we have discussed multiple times, Kp, Ki by S and Kd, this is a derivative filter time constant. Then we can rewrite this equation in this form where K1 and Kt, that means if we simplify, right, if you write the whole expression as a polynomial of numerator and denominator, we can take Ki out, and these are the expression. Next, in the loop compensation, what is our objective? We need to set this numerator 0 in such a way to cancel the denominator pole of the converter. That means, there is a pole 0 cancellation, stable pole 0 cancellation, and that we have discussed multiple times. Then next, that means we will set K2 equal to 1 by omega 0 square, K1 equal to 1 by Q omega 0, and we are also setting ESR 0 we are cancelling by means of this derivative pole. Okay. That is why we are setting tau d equal to it should be tau d equal to RC into C. Okay. Next, that means we have one equation here, another equation here, another equation. For the controller, we have 4 unknown. One is K1, K2, K1, K2, which is again a function of PID controller, tau d. The another unknown is the Ki. So, that means we have 3 equation, 4 unknown, then we need another equation. How to do that? And this is discussed in lecture number 34. Now, if we do this pole 0 cancellation, then our loop transfer function will be just like a gain by integrator. That means, it will be some gain Vin alpha Vm into Ki. So, it will look like a, if you take the gain plot, what will be this? It will be like this, minus 20 dB per decade, minus 20 dB per decade, and the phase will be simply minus 90 degree. So, it will be minus 90 degree. Okay. Next, if you write the polar, that means the complex realization, that means your frequency response, then what will get? At crossover frequency, the loop gain will be 1, and this will give us Ki equal to omega c alpha Vm by Vin. That means, if you choose the crossover frequency, then you will get the integral gain. And phase margin is by default 90 degree, because the phase is minus 90 degree and phase margin is 180 degree minus 90 degree, so it is 90 degree. Now, if we increase Kc omega c, that is the crossover frequency, then this will lead to, that means we need higher integral gain, or it is vice versa. That means, if you increase the integral gain, your gain crossover frequency will increase. And we have discussed in lecture number, that means select omega c, find Ki. Okay. And we have discussed in lecture number 34 that this way of PID controller design has a problem of the model matching, because even the model was not matching much lower than 1/10 of the switching frequency, because it is very difficult to get a first order expression, particularly by means of exact pole zero cancellation, and that we have discussed. There can be alternative approach of PID controller design, because in digital control we are going to use digital PID controller. That is why I am primarily focusing on PID controller, but in analog voltage mode control people use type 3 compensator over PID controller, where we will have an additional pole apart from, that means over the practical PID controller. If you take an additional pole, it will be a type 3 compensator, and that we have discussed in lecture number 35 in our earlier NPTEL course. Now, alternative approach, again the same PID controller, but in this case if you look at the C DVDT in the small signal range, so this is nothing but the capacitor current for the buck converter, and that will be IL minus I0. That means the derivative of the output voltage will carry the information of the inductor current as well as the load current. So that means it inherently provide similar to current mode control with load feed forward. Now we want to take the advantage of this. So that means in order to take, you can use a PID controller and you can view the derivative action similar to your inductor current with load feed forward, and you can set KD to be some, because here you can see C DVDT equal to IC. If you set KD to be exactly C, then it will represent like a current mode control load feed forward, but the larger KD can have some effect because it can actually inject lot of high frequency noise. So that is why we may take a smaller value of KD. Another thing, the time constant of the derivative filter, you can choose T by 2, you can choose T by 10. Okay. So that means this is somewhat flexible. Then what are the design step in the loop shaping? So for this design, you set KD to be, let us say 0.1 times C, you can 0.4 or 0.5 times C, no problem. You can set some tau d T by 2, you can take T by 10 also, and Ki, let us say Ki is the integral gain, and dimensional it is 1 by integral time constant. So it is dimensional, it represents the frequency in hertz. So here it is, we have taken switching frequency by 20. It is also a kind of a conservative approach. Finally, that means you know KD, you know tau d, you know Ki. Now you have to find Kp. So you can get Kp such that you set, so the gain crossover frequency become 1/10 of the switching frequency. By that way you can get the proportional gain, and this approach is far better in terms of shaping the loop, and it will also have a better model matching, and we will be discussing the digital control case study by this approach, indirect approach, in the subsequent lecture with model matching. Now we will be considering boost converter voltage mode control. So again it is the same as the buck converter voltage mode control, only the topology is different. Same thing, we can write the loop transfer function. The only here is that in the boost converter we will have a right half plane 0. Here we are talking about the ideal boost converter. In a practical boost converter we may also have an ESR 0. Since ESR 0 is far right hand side, so it will be primarily dominated by the right half plane 0. And what is VE? It is V in by 1 minus d whole square, and in for a boost converter we know that omega 0 is 1 minus d square root of LC. So all these expressions are well known. Now if we take a PID controller in a boost converter, how to design? Again we write this PID. Again you are initially going for exact stable pole zero cancellation. Again we can rearrange this PID into this form. Now going for the design. So you write the loop transfer function, and we know the loop transfer function of the boost converter. There is a right half plane 0. This is the pole of the converter, and this is the expression of the controller, and we are taking the Ki out here. So that means we have clubbed all the gain here, then all the pole zeros in the right hand side. So our initial objective, we set the numerator stable zeros, controller 0 is equal to the denominator of this, that means the stable pole of the boost converter. Then if you do that, and then we will choose tau d in such a way that this 0 should coincide with the right half plane 0. That means it is a stable pole of the controller which should be placed in coincidence with the right half plane 0 of the boost converter. If you do that, then the total loop transfer function will look like this. Okay? And next it is discussed in lecture 36 in the NPTEL in control and tuning method. Then what we will do? The loop transfer function is written like this. Now, we want to obtain the frequency response, that means you replace S equal to j omega and you can get the expression. Now, I am rearranging by modifying, because here it will be S equal to j omega. So, I am dividing j omega by omega RHP and multiplying here, so that all will look like omega by omega RHP, and then I can realize this loop transfer function by the normalized frequency, where normalized frequency is omega by omega RHP. Okay? And this can be written in the polar form r and theta. What are these? Loop transfer function r is nothing but KL by omega n. What is KL? If you write, so this we have taken KL here, this is the term we have taken KL, that means KL equal to FM, which is the modulator gain of the voltage mode control, that means the sawtooth. What is FM? We know FM equal to 1 by Vm, and what is Vm? It is nothing but the sawtooth voltage peak value, this is by Vm, peak value. Okay. Then we know this is the input voltage, Ki that we need to find, we have not yet designed, and D is the duty ratio, we know then omega RHP0 is also known, because it is a function of resistance, duty ratio and the inductor. Now, once we write it, then we have to design, that means we know the real part of the loop transfer function, frequency response, and the imaginary real part and the angle, magnitude and the angle. Now, what is phase margin? So, phase margin we can write, that means the phase margin is generally 180 degree plus theta of omega n, for this case where omega n should be equal to omega c by omega RHP. That means let us write here bottom. So, I am just writing here, it will be theta of omega n, where omega n is computed at crossover frequency by RHP0. Okay. So, that means if you write, this is the expression. Now, how to design? First you write that means select the crossover frequency based on the phase margin. So, if you set a desired phase margin, suppose I want to achieve, let us say 45 degree is my desired phase margin, then you set this here to 45 degree and solve this tan inverse, and there you will get what is by omega n value for the 45 degree phase margin. Once you get that, then you can, that means that omega n dash, that means what is omega n dash? It is nothing but omega c by omega RHP. Okay. So, that means you will get omega n dash value. So, I am writing here dash, because omega n is just a frequency, omega n dash, or it is already written, sorry, I am saying here. So, it is already written here, because we have written omega n equal to omega RHP. That means in this case omega n dash is nothing but omega c by omega RHP, and that you can find from this expression. Once you find, then you substitute, then you will write what is my Ki, right, because if you know what is my, from here what you will get, that means you can obtain the value from this equation, that means it is known, omega RHP is known. So, omega c will be known, it is known from phase margin, or it is, sorry, it is computed, I will not say known, it is computed from phase margin, computed from phase margin. Once it is computed, then you have to plug in here and find the integral gain. So, that means then in the controller we already know K1, K2 you can find out, and tau d was coming from the right half plane 0, that is the 0, these are all known, and you also know the Ki. So, you know all the parameters, by that way you can design. Now, we are talking about current mode control design for a buck converter. We know this is the implementation of current mode control. We have an inner current loop here and we have an outer voltage loop here, and this is the peak current mode control. Then in the current mode control we know the GVC in the current loop, and if we take a first order approximate model, it will be like this GVC, where these are the function, and this thing we have discussed in our lecture 38, and this is we have to shape the loop. So, what will be the omega c? So, if you do not consider any ESR 0, then it will be this representation is a type 2 compensator. But if ESR 0 is ignored, that means we do not need to consider this. That means omega c will be type 2 for with ESR, and it will be a PI controller without ESR. That means if you ignore this, that means you do not need a controller pole, and if this is not required, then it will be simply 10 by S, which is the structure of a PI controller, and this thing we have discussed in lecture 38. Next, once you do loop compensation, because we are using this cancel with the ESR and this 0 with the pole, so it will look a first order system, and this is RKC by S, where Kc is the controller gain that is coming from here. Then if you do that, you will always get a phase margin of 90 degree, and you have to find out the gain crossover frequency from here. That means phase margin is always 90 degree. Now if we increase the omega c, that means if you increase the crossover frequency, gain crossover frequency, then your controller gain will increase. But we know that we cannot increase significantly, because there is a model validity problem, and we know that model for current mode control will be valid, nearly you can say it should be less than equal to 2 pi FSW by maybe 7 or 8. 1/10 is the very good number, but in current mode control you can slightly increase, and it can go up to, let us say, 1/7 of the switching frequency. So then you can set the crossover frequency accordingly. Now if you take a boost converter, the same current mode control, only the topology got changed, then we can write the loop transfer function. For a boost converter, if you write the control to output transfer function under current mode control, we will get a right up plane 0. And if we take an ideal boost converter, we can drop this term, and these are the expression, it is given in lecture 31 in our earlier NPTEL course. And if you take a current mode control compensation, again you can ignore this, because we are talking about ideal boost converter. If you are taking ideal boost converter, ideal boost, so you can drop the ESR term, and if you drop it, then you need to do compensation. So for boost converter we need a type 2 compensator, where the controller pole will be placed in coincidence with the RHP 0, and the controller 0 will be placed in the stable pole of the converter. And then if you do this, and this is discussed in lecture number 39, then you will get a loop transfer function, which in the polar form it will be written like this, and r omega n KL by omega n, where this is your KL, okay, and then theta omega n like this. Then how to design? This is your r omega n, and the gain crossover frequency r will be 1, so you can get from here, and this will give you crossover frequency is nothing but Kg into Kc. These are the system parameter, and once you, that means this Kc will be the controller gain. That means if you set omega c, then you can find Kc, because this is unknown and this is known, perfectly known. Next, phase margin, it is the 180 degree plus phase computed at omega n equal to crossover frequency by RHP 0, right, and then it will be 90 degree minus tan inverse this. So for a given phase margin, find the gain crossover frequency either by using phase margin criteria, that means you set a desired phase margin, then you can find out what is my omega n dash, which is nothing but you have to find omega c by omega RHP. That means you can find omega c from the phase margin, and if you know omega c, then you can actually find out the controller gain from here, okay. Another way, we can set omega c to be k times RHP 0, and it is well known, we have discussed in our NPTEL lecture number 39, k must be smaller than unity. If k equal to 1, the phase margin will be 0 degree, so it will be unstable. So k must be smaller than 1. If k is small, we typically for current mode control, we take RHP 0 by 3, less than equal to this, but this is for high load condition. Under light load condition, we have to take the minimum of, that means I would say you should take minimum of omega RHP by 3, omega switching frequency by 10. These two are the constant. Otherwise, for light load, if you go for high bandwidth, then your model will be invalid. Okay, and those things we have discussed. So, if you set a k, let us say k you can choose 0.33 like this, then also you can find out the gain crossover frequency right from here, and you can compute the phase margin directly plug in here. So, that means, and it is typically 1/3 is taken, where you will get nearly close to 60° phase margin. So, in summary, we have discussed, we have recapitulated our continuous time small signal block diagram. We have discussed the frequency domain PID controller design for voltage mode control and current mode control boost converter. We have discussed frequency domain PI controller design for current mode control buck as well as the boost converter, and we have also discussed some key design step for analog voltage mode and current mode control. And these are the primary step before going to design digital control, because we will be using this frequency domain approach and we will incorporate additional delay term which will be coming due to the DPWM as well as the the ADC delay, and then we can modify our design step for design the digital voltage mode and current mode control, and that we will be discussing in the subsequent lecture. That is it for today. Thank you very much.